Welcome back, guys. Today we're going to talk about the fourth and final mode of transformations, dilations. Okay, let's get started. Now, dilations or scaling is a similarity transformation, as you can see right there. The last three transformations we've gone over, reflections, translations, and rotations, they've all been congruence transformations, meaning they preserved isometry. Dilation, however, is a similarity transformation. Okay, we're going to be either enlarging or reducing the figures proportionally, fun word again, with respect to a center point and a scale factor. It's a lot of vocab words in that sentence, but it's okay. Remember, scale factor is when we compare the sides of two similar figures. So as a reminder, if I have a triangle, let's just go A, B, C here, and then I have triangle X, Y, Z. This is 4 and this is 8, okay? The scale factor is when you compare the side lengths of each figure. So 4/8 or 1/2. Okay? We'll be using scale factor a lot in this section, and whether the shape is dilating bigger or smaller, so whether it's enlarging or reducing. All right, so only new information is the picture, and that the variable we're using for scale factor is going to be a K. So in all the PowerPoints and in anything else we do, scale factor is going to be represented by a K. Now, let's look at this picture down here. In the picture, we have a dilation with the center C and a positive scale factor K. K, if you can see over here, is 2.5. Okay? Now, C is my point, my center. That's where I'm dilating from. And my pre-image is LMP. Now, imagine this image as though C was like a flashlight, and you're shining a flashlight on the pre-image. Now, the further away from the flashlight you go, the larger the rays get, as you can see with these red dotted lines. They get spread out further and further and further the way they get from the center point. Okay? The closer you get to the center point, the smaller, or the closer those rays are going to be. The further away, the more spread out they are. Now, what we're doing in this picture is we are looking at the distance between the center point and the pre-image and the image itself. So the distance between C and P is 4. Okay, so if I wanted to dilate this by a scale factor of 2.5, as you can see down here, what I'd have to do is I'd have to multiply the distance between C and point P by the scale factor. All right, this would give me 10. That means this distance right here, C to P prime, is a length of 10. All right, now we do the exact same thing with all the other sides. Let's say that CL right here was a 1. All right, well that means that C to L prime is going to be 2.5. Okay, let's say that CM is a 3. That means my distance from C to M prime, all the way out there, is going to be 7.5. Okay, so you're multiplying the distance that C is to the vertex in order to get the vertex prime. All right, let's do a different example off to the side over here. Let's say we have, I don't know, square. Let's go with X, Y, Z, W, okay? There is my figure. And now let's say that my center point is X right here. X is my center point. That means my dilation rays are going out from point X. Ta-da! Okay, so however I dilate my figure, the vertices are going to end up along those rays. Okay, I think I said square earlier, but let's make this a rectangle. Let's say this is 3. Oops. Let's say this is 3, and let's make this 5. And then let's say that K is 2. Okay, so what this means is that x, y is going to be 5, but then we have x to y prime is going to be 10, because we've multiplied that distance. Okay, x to w is a 3, but x to w prime, well, that's going to be 6. Okay, and then if we wanted to find x to z, we would have to find the distance between x and z. Now, in this case, because it's a rectangle, we could probably figure that out using Pythagorean theorem, but we're going to let that stand for right now. You get the picture. Whatever x to z is, in order to find x z prime, you would need to multiply that length, call it y, by the scale factor of k. All right? Now, a bit more vocab. So if k is between 0 and 1, okay, then it's going to be a reduction. You're getting smaller. If k is greater than 1, then that's going to be an enlargement. It's going to get bigger. Okay, so keep an eye on what k is, and it makes sense. If you're reducing the size, if you're reducing the distance between k and, or the center point and the vertice, then it makes sense your image is going to be smaller. Okay, so here's another example of that exact image. Okay, so here we have the pre-image of ABC and a center point of D over here. And then you can see they drew the dilation lines going through A, B, and C. Now what they said is the scale factor in this picture is 1/2. Okay, so it's less than 1, so that's going to be a reduction. So our image should be closer to the center point. And sure enough, as you can see in this image, you have AD right here. But then when we multiplied whatever that distance is, okay, call it 10. We can pick any number we want. But let's just say the distance between AD was 10. That means A prime to D is going to be 5 because you multiplied it by 1/2, and that's how the point A got closer. Well, if we do that to all of our points, we get this picture down here, where A prime, B prime, and C prime are closer to D. And this is a good image of a reduction, whereas beforehand, that first picture was a good image of a enlargement. Now, when we put this on the coordinate plane, we get some rules. Now, as we've mentioned in the previous slide, we've talked about the center point, and the center point is very, very important. Depending on where the center point is, your problem could be easier or it could be mildly harder. If your center point, let's just say let's just go over here. Here's C, our center point, and here's triangle W, X, Y, Z again. Okay? Now, if your center point was just, I'm picking a random point here, 5, 1, okay, on a coordinate plane, you would need to find the distance between C and Z before you could multiply it by the scale factor. Okay, so this type of a problem requires a little bit more work because you would need to find the distance between your center points and your vertices. Okay, however, coming over here, if your dilation is centered at the origin, then you can use this rule. One more time. If your center of dilation is at the origin, then what you can do, instead of finding the distance between the center point and the vertices and then multiplying that distance by the scale factor, what you can do is multiply the scale factor directly to the coordinate, which was something we couldn't do beforehand. Now, this is unique to the center point being at the origin, which for our problems, 9 times out of 10, it's going to be. But keep in mind, in order to use this rule, the center point has to be at the origin. If it's not, then you gotta go back to this method and find the distance between CZ and then multiply the distance by your scale factor. Okay? But what we're going to do is we're going to practice with this rule because that's going to be the large majority of our problems. And so here we go. This would be a good example to have in your notes. This is an image that has a dilation centered at the origin. So we are allowed to use our rule and multiply the scale factor to the coordinates directly. And you can see that happen here. Point J is -2, 4. Multiply the scale factor to each individual coordinate, and then you get 5, 10. Okay, same thing down the line. So blue is the pre-image, J, K, L, M, and then the image itself is J prime, K prime, L prime, and M prime. And if you want, you can even draw the dilation rays starting at the origin, and the dilation rays go through. My angle on the iPad's a little weird. Ta-da! But they still go through the vertices of the image and the pre-image at the same time. Okay? If we were reducing the image, then it would be closer to the origin, and it would be smaller than the pre-image. All right, let's go ahead and practice. What I want you to do is the video is going to pause, and you are going to map out your points. So write out your points and tell me Q to Q prime, R to R prime, and then draw both the pre-image and the image. Go for it. And here is your image and your pre-image. Notice how the image got closer to the origin, which is, of course, our center of dilation, which is why we were able to use the rule. This is a reduction, okay? Our scale factor was less than 1, so it makes sense that our picture got smaller. Now, a different type of problem is when you are given the dilation and the image, and you're told to find the pre-image. Okay, so a dilation with a center of 0, 0, aka the origin. The purpose of this little piece right here is it tells us we're allowed to use our rule. Now we have a scale factor of 2, and the pre-image coordinates are x, y. The image coordinates are 8, -4. Okay, so if we have x, y, I'm going to write out the rule, to 2x, 2y, and we know that our points over here are 8 and -4, well, how do we figure out what our pre-image points were? We divide, okay? If multiplying by 2 got us to our image, then dividing the image by 2 will get us to our pre-image. And here it is. It's going to be 4 and a -2. So you don't really need to graph this one, but this is a good type of problem where it's the same exact information, just going in a different direction. Okay? So make sure you're really familiar with the rules and how the image and the pre-image relate to each other. All right, this is just a brief reminder about the different notations. We've had this on the board as we've gone, but it's always a good idea to have it again. If I want a reflection, I'm going to have a capital R, and then this tells you the line of reflection. So what do you reflect it over? And remember, reflection, there are 3 rules, so make sure you know those rules. Translations, capital T with the vector form. This means that you are subtracting 3 from x and then adding 2 to y. Okay? Keep in mind that's how the vector relates to the coordinate. Now again, rotation, lowercase r. Always assume you're going counterclockwise. And this O right here means the origin. Okay, so we are rotating 90 degrees counterclockwise around the origin, unless told otherwise. So always assume counterclockwise, and always assume around the origin, unless you're told otherwise. And then finally, here's the notation for dilation. You're going to be told, capital D. This is K, my scale factor. And then just like with rotation, you're going to assume you're dilating from the origin, okay? Unless told otherwise. So if they want you to dilate from a different point, it'll tell you within the notation. It'll be like comma, x, y, or something like that. But if you're not told anything else, go ahead and assume that they want you to dilate it around the origin. All right. Last but not least, when you have compositions, remember you're reading them from left to right or from right to left. Okay, you're going to do this one. Whoops. You're going to be doing this one first and this one second. Okay, because that composition notation can be rewritten as a set of parentheses. Okay, and you always do the inside of the parentheses first. All right, that's it for the lesson. I'll see you next time. If you have any questions, make sure you write them down, and I'll see you in class.